Okay. Yeah, we can get started. People can join in as they come, and in the beginning, we'll talk a bit more about some 3D printing techniques. And again, as we get started, as a disclaimer, I am by no means an expert or a 3D printing technician. I have a bit of experience working with it, but a lot of this is like rules of thumb and more of a guide about some things that you should think about. And for greater detail, you can always consult other resources. But at least if I tell you, you'll know some things to look out for. So last week I introduced a few of like the ideas like surface finish, like the fact that when you build up material layer by layer in the form of additive manufacturing, you often can't control your surface finish to as much of an extent as you can with other techniques. And with that, there also comes problems with like layer adhesion, which can cause maybe weaknesses in terms of mechanical strength, which can be a consideration if you're designing a part for something structural, like an arm for a robot, for example. In addition to that, there's some like aesthetic considerations in terms of how you want your printed part to look. But if you're just making like a model for a hobby and it's not going to be under a lot of load, you can usually just post-process what you print by like sanding it down and painting it or whatever you do. So there's that. This week, here's some of the topics we'll talk about. One of them I mentioned last week when I told you what you should think about when you design your keychain, which is the final project. And this was the minimum thickness of the part's geometry. So the thinnest feature that exists in your model, that's kind of determined by the 3D printing instrument that you're using. Other things, like I guess mechanics of 3D printing, other topics, and new technologies that exist that are kind of related to 3D printing or like new forms of applications of 3D printing. So we start off here with our discussion on minimum feature thickness. And this is actually something you should think about even if you're not doing 3D printing, even if you're designing a part for conventional manufacturing. For a variety of reasons, you want to make sure you're aware of where your minimum thickness wall or feature is and whether or not that's acceptable. So for 3D printing, as you may or may not know, this is kind of an example of a nozzle that you would find on the extruding head of the 3D printer. So the way it works is you have a big spool of wire, usually of plastic material of the substrate, and that gets heated up at the nozzle, and in the kind of liquid phase, it just is extruded out and onto your part, onto the work. So as you can imagine, in that case, the size of the nozzle here, it's marked out as 0.4 millimeters. That kind of determines, for one thing, how thick the layer is going to be, because when I talk about extruding, you can think about what we do in Onshape when we use the extrude feature. It's essentially squeezing out a material in the same cross-sectional shape as the shape of the nozzle. So when we extrude things, we select like a sketch region and we kind of push material out in the same shape of that cross-section. And so what you're going to get is a layer thickness that is more or less, it's not exactly the size of the nozzle, but it'll be related to the size of the nozzle. So larger nozzles will produce thicker layers, finer nozzles can produce thinner layers, as well as the minimum part thickness. So you can imagine if I have this 0.4 millimeter diameter nozzle and I'm trying to create a feature that's, for example, like I'm trying to make a wall that's 0.2 millimeters thick, that just isn't physically possible because the geometry is smaller than the instrument, the process itself. Another thing is that if you're trying to create a part that's too small for the printer that you're doing, you can get like pretty low quality prints just because the size of the layer thickness becomes significant compared to the size of the part itself. And the layer thickness isn't really something that you have too much freedom or control to choose just because it's determined by the printer that you're using. And I also mentioned again that this is a relevant consideration outside of 3D printing, even when you're not creating material or you're not creating a part by extruding from a nozzle. For example, when you're machining something, you often you often want it to be that you don't have any walls that are too thin or else they might break. I might show you a picture of what I mean if I can find one later on, but I'll come back to that. I'll try to come back to that. Another thing we have is something called infill. So in most applications, you don't actually print a entirely solidly filled part. So let's say that we're trying to 3D print just a cube. And what you're going to see is that it's kind of wasteful material to print out the entire cube because the volume of the plastic substrate that you need to use is like the volume of that cube. If it has a solid length of S, then it's S cubed. So in most cases, you don't actually need a solid block of plastic. You just want a cube of plastic. And so you can get away with just, first of all, you need to have the external part. You need to have a surface on all the cube faces. So you need to print at least that much. And then for structural integrity, you also need to have some material inside just so the cube won't be crushed by the slightest touch. So here's some examples of different geometry. On the right is a photo where you can see inside of a, I guess, perhaps it's a demonstration part or they just stop the printer midway through, but you can see this is a very fancy type of infill shape where they have multiple of these like sinusoidal waves in orthogonal directions. And what you see is that most of the interior is just full of air. It's just gaps. And you can imagine that in compression, in tension, in torsion and shear, this is a fairly strong material. Sorry. So it's a fairly strong, still finished part, but despite that, it uses less material. I think you understand what I'm getting at. So in terms of what you control, when it comes to programming your 3D printer, so to speak, you use something like, you use a program, usually something called a slicer or like a CAM package. And in there, you can specify parameters, for example, including infill. And you can tell the computer what % of the part by volume you want to be filled. And that computer will post some code that the 3D printer will read, and the 3D printer will know what patterns to create. So there's some other common examples. I think you see some honeycomb often. I think that's the one I've seen. And of course, this isn't to say that you never print a solid block of material when you're 3D printing, because for some applications, you're going to be modifying the part after you print it. One classic example is when you're tapping threads. This is when, for example, you want to put a screw into your part. Well, the screw has these threads on it, and the threads need to go into something. In most cases, it's not like wood where the screw kind of taps its own threads as you turn it for the first time. You kind of need to already have something like this, these grooves, so the thread can just turn into them. So if you're doing something like this, obviously, well, maybe not obviously, but you need to have some solid material. And if you're planning to do this to your part after you print it, then you would need to specify that at least a certain region of the part needs to be solidly filled. So there are some like instances where you do have this. Next, benchmarking. This one's actually, in my opinion, pretty interesting. When you have a 3D printer or any manufacturing device, you have to kind of drop the assumption that it's going to produce perfect parts, because even if you program it perfectly, you give it the geometry and it knows exactly what to do, it's not going to create a perfect geometric replica of the thing that you created in CAD. And that goes for no matter how expensive your machine is, no matter how well it's calibrated, there's always going to be a small amount of error just because of the facts of real materials, right? So if you're ever curious about how good your 3D printer is, people design these artifacts, these models, which are designed to demonstrate how good your 3D printer is at doing certain features. So on this example here, the first thing you might notice is these two overhangs, and they consist of a number of like angled walls at successively increasing angles. So if your 3D printer is able to reach this angle, then you'll get a very high quality print even at the edge of this kind of curved beam. If your 3D printer is not capable of doing this, then you'll either fail to print the end of this beam or it'll just look pretty bad. Likewise, there's some other things. There's some like tall columns that are very thin. There's some very thin walled cylinders, which let you look again at like your minimum wall thickness. You can inspect the quality of like your lettering on vertical faces, on angled faces. So there's a lot of different benchmarking artifacts that people design. If you remember from, I think, class 4, we talked about like Thingiverse, which is a place for hobbyists and 3D printing and CAD people, where they post things they do. So if you search like a benchmark artifact, I'm not sure what the common name for these things are, but people design these kinds of objects that just have interesting geometry that will reveal something interesting about the quality of your 3D printer. So something like this, right? And you'll be interested to know this is actually done in like, not just by hobbyists, but this is a practice that is done in industry and in research. Whenever people have a new machine that can create parts, of course, this is like in my opinion, a pretty clever way to see a lot of different facts about what your machine is capable of. This one I think we discussed before. It's the failed prints. So there's a lot of reasons why a print can fail. Some of it is your design error. So if you're not aware of this kind of thing, like if you're not aware that your printer is not able to do an 80-degree face, and you design a part with an 80-degree face, and when you set up your printer code, you orient your part in such a way that you create an 80-degree like face that has an overhang, so it's just floating over air. And then after that, you also do not create any support material underneath as a temporary like support for the 3D printer. In that case, you've made kind of a poor choice, and that can lead to 3D printing errors. Another thing is like how big you're printing, especially for these larger prints, or you make something that's just not suitable for the specific machine that you're using, and you just don't notice when you're trying to post your code. That's something that can happen. And a lot of the cases, especially for 3D printing, where there are a lot of like lower end, cheaper 3D printing models available, you might run into actual printing error where the machine itself has some kind of defect or error. So a lot of the times, some people will say that like with a good operator, you can make like the machine will do its job, and it's something that the operator could have prevented. But especially when you are newer or you don't know what you're doing, it's a lot of the time like something you just have to experience once and learn what happened, and after that you'll be better at using the machine. So things like this, where you have stringing, you have poor adhesion, maybe there's some error with like machine or the environment that it's in. Sometimes you just have to learn from your mistakes. In terms of 3D printing, there's also like a lot of research that's done in terms of 3D printing, as well as novel additive manufacturing techniques that are not technically 3D printing, but are like similar in philosophy to 3D printing. So I guess some things that you may have read in the news a while ago are the concerns about people 3D printing parts for weapons, for firearms. So that was like a big issue. If you're interested in that kind of thing, like ethics and technology, that's definitely an interesting thing that you can read up on. Another thing is the concern over intellectual property rights, because back in the day, I guess if you have some kind of design for a physical object, let's say, I'm not sure, like some desk implement, like a cup holder or something, it would be pretty difficult for somebody to just see a really cool cup holder that they like, and then to create a die and injection mold their own version of that cup holder. But now that we have 3D printing, any person can perhaps even like download a CAD or try to recreate the CAD and then end up printing the thing for themselves. And so that raises a lot of question about like if someone owns a patent or something like that, like only one person has the right to like sell this type of product, but other people are able to recreate the product using 3D printing. That's also another like societal issue that you can, if you have an interest in such things, you can read up about. Another thing is that 3D printing, as cool as it is, a lot of the time it's not used in a lot of industrial or commercial applications. Now, that's becoming less true as you see a lot more like commercial products that are being made with 3D printed parts, but in most cases, like my computer mouse, for example, like you're not going to see the casing for that be 3D printed. It's just that they're a lot more cost effective and, or at scale cost effective and more accurate ways to create most parts. So people are still working on how to improve 3D printing as a technology, just so that we have access to more materials, that we can create things that are stronger, that are more accurate, and can be cheaper and faster. Other things that are being developed or are newer, I guess, fields of study are metal 3D printing, I guess metal additive manufacturing in general. There's one process called laser powder bed fusion, which I think is really cool and has been used to make actual parts on I think I read that this was used to create part of a rocket for SpaceX, but I may or may not be accurate. So it's not quite like 3D printing, but instead of like extruding a material, use a laser on a bed of powder, and the laser will melt just the parts of the powder that like it touches, and from there you can build up layer by layer just by adding another layer of powder, melting the areas you want with the laser, and then building up again. So in philosophy, it's a lot like 3D printing, but it's not quite 3D printing. There's also like laser sintering and similar processes that allow you to create things out of metal in a similar fashion to 3D printing. Another really interesting thing is printing of composites. So composites refer to usually materials like carbon fiber, Kevlar, I guess nylon as well, where you have multiple like materials kind of in a weave, and they're very, very strong in certain loading. So a lot of things you see, like a lot of racing vehicle, like monocoques are made out of carbon fiber. And so the process for making these is kind of like very time and labor intensive, because you need to create like a mold and then do your layups over the mold, and you need a lot of time for that to like be prepared and processed. But with 3D printing, perhaps it's possible to print like carbon fiber directly without having to go through the whole layup process. Some more fun things, there's like 3D printing of food. I think this is chocolate that's been 3D printed. And of course, there's also like medical applications where here it seems that they're printing some kind of tissue in some sort of medium. I don't really know anything about these pictures, but as you can see, there's a lot of future in terms of research / industry side 3D printing / additive manufacturing type techniques. So with that, if you have any questions about 3D printing, again, I'm not really an expert in this. I don't know too much about 3D printing, but feel free to ask any questions. After this, I'm going to give you most of the time to kind of work on your own. I'll do a little demonstration for one more thing you can do with the project 3, which I introduced last week, and then I'll give you some time to work. And at the end, maybe you can have each other, like if you want, you can screen share like what you've made. We have about like 40 minutes at this point. So I'll take some questions and then I'll do a short demo, and then I'll give you time to work. All right. Then last week I introduced this project, and maybe some of you have started, maybe you haven't. Either way is okay. Again, the objective here, we're trying to make some kind of like keychain attachment that you may have seen. Like you probably know what I'm talking about, like a little small trinket that goes into your keychain loop and you put your keys on it. So just as you continue to work on this, keep in mind things like the minimum thickness. I'd say don't go any smaller than like 2 millimeters, just so you have like a few layers at the thinnest part. And other things like if you're, I guess a lot of the things that you would be considering are more at this end of when you're like actually trying to post the process to the 3D printer, but even in the design, it's good to think about these things. So I'll go into Onshape. Hopefully you still have this up. You know, we haven't been doing a lot of intense CAD this past week, but there's one interesting technique I'd like to show you, and let me see. I don't know how to spell silhouette apparently. Silhouette, okay. One thing that you can do in Onshape is in a sketch, you can actually let me see, image, insert image. So I'm not sure if this tool is in your guys's like toolbar. It doesn't seem to be in mine, but that might just be due to the size of my laptop screen. If you ever like, by the way, if you ever need to like find a tool and you don't know where it is, at the end here, there's like a search bar. So if you know what it's called, you can just search it up, and it's actually here. So you can drop down from here and find insert image, or you can just search for it. But as you can imagine, this tool lets you insert an image into your sketch, and that's useful for a number of applications. Let me see. And so, yeah, you first have to like import the image into your workspace, I believe. And the way you can do that is just like you imported step files from the plus sign, you hit import, and it'll prompt you to download or like select a file directory. So you do that just like you did to download like the air engine parts if you did that. And what it'll do is put the image into your workspace. So now this JPEG or PNG, whatever it was, the stock image is now in my workspace. And what I can do with this is I can put this into my sketch. So I have my sketch open here, and right here, in this tool that looks like a file with an arrow pointing into it, there's this insert image tool. And what I can do now that I have this file inserted is click on that, and tells you to draw the image rectangle. So I'll just draw a rectangle, something like this. And from here, it's a lot like the text tool that I showed you last week, where you can draw like text using the text tool, and you can control the size of the text with this rectangle. It's like that. You have an image and you control the size of the image with a rectangle that you can dimension. So you can do that. And from here, what you can do is, last week I went over the spline tool, and I guess what's cool is you can kind of just go around and trace the image. And what you'll end up as you do this is you'll actually have a sketch feature consisting of a bunch of splines that resemble the shape of whatever thing you're trying to trace. So as a CAD technique, this is not ideal for most situations where you need accurate parts that actually like interface with something or something like that. But even when you are designing something, like let's say someone hands you a bracket, like for example, you're trying to mount a GoPro and the bracket has this weird bolt pattern on it. If you don't actually know what the bolt pattern is, one thing you can do is just take a really accurate scan or a picture of the physical object, save that as a picture. You can just download the picture and try to recreate it in a manner such as this. But for our purposes, we're just making like a keychain for fun. So it's not too critical what the exact shape ends up being. But what we end up doing is something like connect the dots and finally I go around and I get to the end and you can see that my sketch is of a cat. And what I can do is extrude this region that I just created. Now, without having, just starting with that stock image that I found online, I now have like a somewhat low fidelity copy as a cross section of a 3D model. So feel free to try to do that as you're designing your keychain. One thing that I would point out here is like, look at this and then ask yourself, okay, where's my minimum part geometry thickness? So when I look at this part kind of concerns me. I see that the thickness of this might be a bit thin. And so hopefully the measure tool may or may not let me just measure the thickness. It does not let me measure the thickness, but if I do something like this, I can just create another sketch, let's say here, and what I can do is just put a couple points on where I want to measure, like here and here, maybe for, I guess that's not where it's thinnest, maybe like here and here. I think it's very thin between these 2 points. So I just put the sketch points in and now I can measure it based on these points. And I see that the minimum distance there is 15 thousandths of an inch or 0.015 inches. So I'd say that's rather thin. I wouldn't try to print something like this, although maybe it'll be fine. Another drawback is that even if your printer is physically capable of producing this geometry, it's going to be super thin. It's probably going to break off after you handle it for a while. So that's a way that you can like test things like that with the measure tool and applying some extra points. But yeah, for next like 10, like 15 or so minutes, I'll just give you some time to work on your own on this keychain project. If you have any questions about what you're doing, about the CAD or about 3D printing in general, you're free to ask. But I'll let you work for a bit, then we'll reconvene. I'll let people screen share if they want to share. You don't have to if you don't want to. And then there'll be some final words before I conclude the class. Yeah, so at around 5:15, I might have us come back together, and if you want to share, I'll let you share, and I'll go back to talking for a bit. It'll take another few minutes. All right, so if I can get your attention back from whatever CAD you're working on, is there anyone who wants to share what they have or what they have so far? And it's fine if you're not finished. It's not that much time to work on it, but maybe if you want to say in the chat like what you're trying to do, like, write your name on it or maybe some kind of shape. And feel free to just take the screen share. I'm not screen sharing right now, so you can just go for it. All right, someone's making a car. And the thing with that is like, you don't have to feel limited to just make something that is basically a 2D shape that's been extruded. So it's basically a prism. You can definitely 3D print things that are of a irregular, or like not irregular, but like a actual three-dimensional geometry. All right, so no need to share. I know it's not everyone's favorite thing. I will, from here on, just like talk for a bit and then wrap up the class. So one thing I do want to call us back to is the part where I talked about how minimum wall thickness is important even outside of 3D printing. So this was something that I was trying to make, like I think last week. And you can see here that in the geometry, there was a very thin wall that occurs. And so what ended up happening is I milled the outer contour of the shape first, and I was left with what would become a very thin wall. And then when I tried to drill through it, it ended up just blowing out the material here. So I no longer have a flat surface here as I originally wanted. So whenever you're designing things, just make sure not to be like me and design very, very thin, very thin walls, just because no matter what manufacturing process you're making, whether that's like milling or turning or 3D printing or injection molding or laser cutting, it's always gonna have some issues. Another thing is you might be wondering, like, how do we get from my CAD here to a 3D printer? Like I said, if you're working with a 3D printer, there's probably somebody around or a manual that'll tell you exactly what to do. But as a general guideline, what you do is you take your part, you export it. You usually use the .stl format. You name your file here, cat keychain. Most of this you don't have to worry about, and then you just have it download. You download the file, you end up with a .stl file. And what we can do from there is you'll have some kind of slicer program. So I guess I have Fusion, but I don't have like a dedicated slicer program because I don't do much 3D printing. But there are a lot of free 3D printer, what's called slicers. So you can like look into that online. There's good free ones out there. And they'll basically look something like this, where you have some kind of interface where it allows you to specify a bunch of parameters related specifically to the process. So it's not going to necessarily change the model or the geometry, it's just going to change the way that the 3D printer will try to make the thing that you designed. So you can see here, there's like some examples. I think percent infill, yeah, here, well now. There's definitely more options than this, but it's just an example of what it might look like. So it's kind of the process. You would take the model, you put it into your slicer program. From the slicer program, you'd put in all these parameters based on how the machine should behave. Then from that program, you can post the code, and that'll create like a sort of text file that has all the machine readable instructions that the machine will follow. You plug that into the machine, you set it up, and it runs, and it carries out your instructions. Most printers actually use something called G code, which is also used for a lot of CNC or computer numeric applications. So actually, currently I'm taking a class where I learned a bit about how to write G code manually. But this is a pretty useful thing to learn if you're really interested in like manufacturing. So this will definitely come up later in your life if you are very hardcore into manufacturing. That might be a bit like obtuse if you haven't actually used the machines. Other things, as final words, if you want, you can post. I made a Google Classroom submission, so if you want me to look at it, you can submit a file of your keychain design. It's not all that important. I think in the past, for this class, we actually printed the keychains. I don't know if that's going to happen this time around. I guess in terms of other things, So this is a CAD class primarily. So if you're interested in CAD, what I'd recommend always is just to practice. The way you get good at CAD is to practice, and the way you practice is usually you just find an object that you think has an interesting shape. And even if you think it's like a really hard shape to make, or you have no idea how you go about making the shape, the way that you learn is like by picking things that you don't know how to make and then figuring out how to do it. So if you're in Onshape, like Onshape has really good documentation. Well, it has documentation that is pretty good, and not documents, but like even here, this is the documentation. So you can like search for like help content and try looking on forums as well. If you want to move past using Onshape as your CAD program, in terms of free CAD programs that are available, I think I guess it depends on, at this point, you're all students. So I believe that as a student, you can get a free like student license to use Fusion 360, which is another like program that has like a CAD package in it. So what you'll see is that there's a lot of differences between different CAD packages. So like Fusion 360 and Onshape is very different, but a lot of the principles, the ideas of like creating a sketch, having constraints in the sketch, fully defining your sketch, and then extruding or revolving or doing all these things, those ideas are all the same. So it's just a matter of learning a new interface and a few different tools. So this is a good place to like start if you have no idea where to go from here. You can also like ask your school if like they have other CAD packages available to its students. So like as you go into like high school, they definitely will have like computer labs with different CAD programs on it that you can try to use. And it's just generally a useful skill. Also, for like this like AOE program, I also helped to make the next classes, CAD 3 and CAD 4. So to give you like a peek at what we do in those classes. I guess CAD 3 is kind of different in that it's focused a bit in the like mechanical design or specifically like a robot type of application, but if this ever opens up, hopefully it does open up. Yeah. This was like the project that we did for the CAD 3 class. So you end up making like a little drivetrain. You do some selection design with like downloading like off-the-shelf parts. You're working with like an assembly that does a bit more interesting stuff. Shoot, okay. Seems like Onshape does not like loading this assembly, but that's what we did in CAD 3, and then in CAD 4, this one is much more like pure CAD focused. So every week I just give you a few challenges to work on, and you just during the class try to recreate that. This is a banana. I think there's some interesting ones. I remember it was a lot of fun to come up with things, the challenges for each week. So it's like a dodecahedron, like geometric shapes. And the cool thing about these is that they seem pretty easy, but as you start to get into it, it actually is a lot trickier than it may first appear. And these are things that you can like try on your own, even if you don't end up doing the class with this program. This one in particular, it's very deceptive. You'd think it's very easy, but it's a bit more involved than you might think. And the great thing about CAD is that like as long as you have like some software, some package like Onshape, perfectly serviceable. It's really, you have all the power in the world to learn how to do whatever you need. So one cool resource I think is this thing called SolidWorks Model Mania. It's a competition held by Dassault, which is a company that makes CAD programs like SolidWorks. And what you'll find is that like they have this convention, and every year they have like a challenge at that convention for people to create CAD models as fast as they can based on a drawing. So for example, this is the very first one they had. They'd give you a drawing that looks like this, and it's your job to create the model in CAD as fast as possible while still having like a robust model that can be changed. So if you ever like are out of ideas for ways you can practice, this is a great place to practice. I remember when I was learning how to CAD that I used this and just like pick random models, try to CAD them. Some of them are easier, some of them are harder. I think this one is a pretty decent one to get started on as well. But yeah, that's just SolidWorks Model Mania. You can Google that. Otherwise, that's pretty much all I have for this class and the whole session. So thanks for coming to class. Thanks. Hope you learned something useful, and maybe I'll see you again in a later semester, maybe like in the winter when I come back to teaching again.